This is your presenter Asloob Mudassar, and I am presenting slide number 69 of the course on laser physics. Question is, discuss the selection rules related to stimulated transition in a bulk semiconductor material. The answer is, the interaction Hamiltonian when an electromagnetic wave of frequency nu interacts with a bulk semiconductor material can be written as, so H prime is the interaction Hamiltonian is equal to dot product between mu E, which is the electric dipole moment of the atom, with a dot with the electric field of the wave. So mu E dot capital E is actually the dot product between the electric dipole moment of the material and the electric field of the incident beam. And this product, the electric dipole moment can be expressed as minus E R, and then we have a dot product with capital E, where capital E, which is the electromagnetic wave, can be expressed as E is equal to E naught e to the power iota k dot R minus omega t, where k we have used a subscript W with k because this is the wave number of the incident wave, so that's why we have used kW. So kW dot R minus omega t is the phase factor of the incident beam, and the whole incident beam is capital E is equal to E naught multiplied by the phase factor e to the power iota kW dot R minus omega t. This is the incident wave at a position r and time t, and omega is equal to 2 pi nu is the angular frequency of the light. So our input frequency, our input beam, that is incident on the semiconductor material, has a frequency nu. If nu is greater than or at least equal to Eg, that is the band gap energy, divided by H, a transition may occur from a state in the valence band to a state in the conduction band. So you see that this, if we have Eg over H, if you multiply H on both sides, you have on the left hand side H nu, that should be greater than equal to Eg, band gap energy, and E and H nu on the left hand side will be equal to the photon energy of the incident beam, and that should be at least equal or greater than the band gap energy, so that the transition will take place, because the energy difference between the valence band and the conduction band is represented by Eg, which is the band gap energy. So if the frequency of the incident wave is greater than equal to Eg over H, a transition may occur from a state in the valence band to a state in the conduction band. Let us designate energies corresponding to these states as E1 and E2. That is, E1 is a state in the valence band and E2 is a state in the conduction band. So initially the electron is in the state E1 of the valence band, and we want to move the electron from the state E1 of the valence band to the state E2 of the conduction band. The transition rate W following equation number 36.12 is given in equation number 69.1, that is capital W is equal to pi by 2 into absolute square of H12 prime divided by H bar square and multiplied by delta of delta omega. You see that we are talking about the transition rate, and in the question we have mentioned the stimulated transitions. Stimulated transitions could be stimulated absorption or stimulated emission. Here we are concentrating on the stimulated absorption, because the stimulated emission will follow the same rules. So we are going to discuss the stimulated absorption. That's why we have used subscript 1,2 with H prime. So H prime 1,2 is actually the interaction Hamiltonian for the state for the transition from state number 1 to state number 2. And O is what we have written because this interaction energy involves also the Hamiltonian of the semiconductor material, the Hamiltonian of the system, without the interaction of the electromagnetic wave, and then of course 1 to O prime means that we have also involved, we have also written this H prime for the atom which was unperturbed, that is which was without the influence of the electromagnetic wave, and then we have written the H prime factor, because H prime also involves H naught, where H naught is the Hamiltonian of the system in the absence of the electromagnetic wave. So here we have W is equal to, if you consult slide number 36, you can come across more detail about interaction Hamiltonian H prime 1 to 0 there. So we have written over here the transition rate W for the absorption system. So we have W is equal to pi by 2 absolute square of H prime 1 to 0 and divided by H bar square and multiplied on in the numerator by delta of delta omega, where nu naught is equal to E2 minus E1 over H, where nu naught actually the frequency that is required to carry out the transition from state 1 to state 2. So we have written nu naught is equal to E2 minus E1 over H. This is the transition frequency between the two states. That is, if we want to carry out the transition from state 1 to state 2, we need a photon of energy H nu naught. And this H12 prime, that is the interaction Hamiltonian, can be specified as interaction Hamiltonian written on the left hand side is equal to the integral of psi star of V, that is the psi star, that is the complex conjugate of the wave function corresponding to the valence band, multiplied by the H prime, which is the interaction Hamiltonian, and then multiplied by psi c, which is the wave function of the system for the conduction band, and integrated over the whole volume, where the block wave functions corresponding to the state 1 and state 2 are respectively given by. So we can represent these wave functions psi v and psi c, that is the wave functions for the valence band and for the conduction band, can be expressed as given in equation number 69.3 and 69.4. So we have psi v as a function of r is equal to u v k as a function of r multiplied by e to the power iota k v dot r. And here you can simply represent u of v simply by uv. So we have simplified this one as uv as a function of r multiplied by e to the power iota kv dot r. And for the second equation, that is for the conduction band, we have written psi c as a function of r is equal to uck as a function of r multiplied by e to the power minus iota kc dot r. Notice that there is a negative sign when we are writing the wave function for the conduction band, and there is a positive sign when we are writing the wave function for the valence band. And here again we are representing the special part uck simply by uc as a function of r, and then of course the phase term e to the power minus iota kc dot r. So we have expressed the block wave functions for the two states, that for the state 1 in the valence band and for the state 2 in the conduction band. Here uc is equal to uck and uv is equal to uvk are the spatial parts of the respective block wave functions. The transition rate w will be non-zero only when the frequency nu of the incident wave matches with nu naught. Because you see that if the frequency of the incident wave does not match with the frequency of the transition, which is nu naught, because nu naught is the frequency that is required to carry out the transition. So if the frequency of the incident wave is not matching with the required frequency nu naught, then of course no transition will take place, and in that case the transition rate W will be 0. So because for the two states, which is E2 minus E1 should be equal to h nu, where nu is the frequency of the incident wave. If this condition is satisfied, where E1 you know that is any level in the valence band and E2 is a level in the conduction band, and we are moving the electron from the valence band with the state E1 to the conduction band with the state E2. So we need input beam with a frequency of h nu, and here you know that this nu is exactly the same as nu naught. Then of course the transition will be carried out and W will be non-zero. This is referred to as the energy conservation rule. It can be shown that the integral in equation number 69.2 will be non-vanishing only. That is, this integral will be non-vanishing only when Kc minus Kv is equal to Kw. That is the difference in vectorial form of the wave number between the conduction band. For the conduction band to the valence band, that should be equal to the wave number of the input wave. So if this condition is satisfied, then of course this integral will be non-zero, and otherwise the integral will be zero. Because you see that we have produced a condition under which the integral will be non-zero, that is h12 will be non-zero. So if h12 will be non-zero in equation number 69.1, then of course W will be non-zero. So it means that there will be some transition rate W which will be non-zero, and that would require this condition to be fulfilled, that is Kc minus Kv should be equal to Kw. The integral contains an exponential factor of the form. So you see that if we solve in detail the integral, that is substitute these values of the wave functions in the integral, we would notice that there would occur a term which is e to the power iota Kc minus Kv minus Kw dot r, which oscillates rapidly with r. The integral will be non-zero when this averages to zero. We can, because you know that if you bring the Kw on the left hand side, then of course this will be zero, and this should average to zero, because for that this is required for this integral to be non-zero. That is W12 prime should be non-zero, which means that W12 prime H prime 12 prime will be non-zero, requires that means that W will be non-zero. Okay. So the integral will be non-zero when Kc minus Kv minus Kw averages to zero. We can rewrite the above equation as, so multiplying both sides of this equation by h bar, we can have h bar within parentheses we have Kc minus Kv in vectorial form, and on the right hand side we have h bar multiplied by Kw, and Kw is again in the vectorial form. So this equation has been written in vectorial form, where h bar Kc is the momentum of the electron in the conduction band, h bar Kv is the momentum of the electron in the valence band. This equation says that the total momentum must be conserved in a transition, because the change in momentum is provided by the input beam on the right hand side, as you can see h bar Kw. So if Kc, Kv and Kw all in vectorial form are in the same direction, here we are treating as a special case the equation in the magnitude form then given by. So you see that if we have Kc, Kv and Kw as a special case, if all these wave numbers are in the same direction, then the magnitude form of equation number 69.6 is given by h bar within parentheses we have Kc minus Kw, and then we have h bar Kw on the right hand side. This is the same equation as 69.6, but in magnitude form, assuming that all the wave numbers, that is Kc, Kv and Kw are in the same direction. Kc does not differ from Kv, and we can write, you see that this equation holds only in the magnitude form, that is the magnitude of the wave number in the conduction band is equal to the magnitude of the wave number in the valence band, because there is only a very slight difference in magnitude between the two quantities, and we can roughly set the two wave numbers in magnitude forms to be equal to each other, as given in equation number 69.7. This is referred to as the K selection rule or K conservation rule. So you see that we have obtained one rule for the transition. First of all, we mentioned this rule, as given in equation number 69.5, because this was required for this integral to be non-zero, and when this integral will be non-zero, it means that h prime 1 2 will be non-zero, it means that w will be non-zero. So this can be interpreted in the magnitude form as kc is equal to kv. So this condition will ensure the same thing as we have just mentioned. This is referred to as the K selection rule or K conservation rule. There are no interactions between the wave and the spin of the electron. So you see that during the interaction, when we move the electron from the valence band to the conduction band, the electron would not interact with the spin of the electron, with the spin of the system. That is, the wave will not interact. It means that the spin of the electron would not change when the transition occurs. So it means that the spin of the electron in the valence band will be the same as the spin of the electron in the conduction band. That is, we can say that the electron spin remained unchanged during the transition process, and we can say that the difference in spins, which is given by delta S, is equal to S1 minus S2 mod, that is the spin of electron in conduction band, and minus the spin of electron in the valence band. This delta S will be equal to 0 because both spins are equal. So you see that now we have two rules. One rule is this, which we call as the K rule or the K conservation rule, that is Kc is equal to Kv. This is the one rule that is required for the transition to take place. And the second rule is that delta S is equal to non-zero, because this rule means that the transition probability will be non-zero, and this rule implies that the spin of the electron will not change when the transition occurs. So this is a selection rule governing the transition. In semiconductor, the main broadening mechanism is based on electron-phonon dephasing collision. So you see that we have mentioned in case of single atom, that is the broadening could be homogeneous broadening, it could be inhomogeneous broadening at the same time. But here you see that in semiconductor materials we are talking about the broadening mechanism due to electron-phonon dephasing collision. We can simply call it as electron-phonon collision. But we have used the word dephasing, which means that the phase coherence of the quantum state is disrupted in this collision. That's why we have just to mention that it also involves with the coherence of the quantum states, that is the phase coherence of the quantum states. That's why we are mentioning the word dephasing. Otherwise you can simply say that electron-phonon collisions. So you see that the main cause of broadening in the semiconductor material is due to electron-phonon dephasing collision. The Dirac delta function should be replaced by a Lorentzian function g of nu minus nu naught, with the function full width half maximum is delta nu naught, and delta nu naught is equal to 1 over pi into tau c. So you see that we are going to replace delta function. Where is the delta function? You see that the delta function appears over here in equation number 69.1. So we are going to replace this delta function with the function g of nu minus nu naught, as we have mentioned over here, g of nu minus nu naught, because you see that g of nu minus nu naught represents the broadening, and in case of single atom it represents a homogeneous broadening. So you see that here we are assuming that due to electron-phonon dephasing collision, the collision that occurs is of the type of homogeneous broadening. So that's why we are replacing that delta function by g of nu minus nu naught, and this delta function, this g of nu minus nu naught, which represents the homogeneous broadening even for the case of semiconductor materials, has a full width half maximum given by delta nu naught, and this delta nu naught is equal to 1 over pi into tau c. That is, pi and tau c both are in the denominator, where tau c is the average electron-phonon dephasing collision time. You can simply call it electron-phonon collision time or electron-phonon dephasing collision time. From equation in question number 36 and question number 40, that is, you can consult slide number 36 and slide number 40. The result obtained for the case of isolated atom can also be extended to bulk semiconductor material without proof. The following relationship will be useful. Now you see that having said that for the case of a bulk semiconductor we can adopt the same mathematical equations that we have derived for the case of an isolated atom, and we are not going to give the proof for this one because the proof is lengthy. So we are just mentioning over here, and you should take it granted that we are saying that we are using the same equations as used for a single isolated atom, even for the case of a bulk semiconductor material. The following relationship will be useful, as we have mentioned this one even for the case of isolated atom, that the average value of the absolute square of h prime 1 2 is equal to 1 over 3 times absolute square of E naught multiplied by the absolute square of mu. This 1 3 comes from the average value of the cosine function there. And we can represent the absolute square of E naught by the I, which is the intensity of the input beam. So we have on the right hand side 1 over 3 multiplied by I, which is the intensity of the input beam, multiplied by the absolute square of mu, which is the magnetic dipole moment of the semiconductor material involved in the transition. So we can write equation number, we have also introduced in these equations, that is in slides number 36 and 40, that rho, which is the energy density of the beam, is given by n square into epsilon naught into E naught square divided by 2, where E naught is the, we have mentioned previously that E naught is the magnitude of the incident beam. And the intensity of the beam can also be expressed as I is equal to C into rho over n. And delta omega, which we have in the very previous equation, that is over here in equation number 69.1, we have delta omega over here, which we say that we can replace for the case of homogeneous broadening, as we are assuming it to happen for the case of semiconductor material. We shall replace delta of omega by the function g of nu minus nu naught. That is this function g of nu minus nu naught. So let's solve delta of omega is equal to, can be written as delta of omega minus omega naught, and omega can be written as 2 pi nu, and the omega naught can be written as 2 pi nu naught. So we have 2 pi common within the delta function, and if you take 2 pi common, 2 pi outside the delta function, it becomes 1 over 2 pi and then multiplied by delta of nu minus nu naught. And you see that, as I said earlier, we shall replace delta of nu minus nu naught by the function g of nu minus nu naught. So making these changes as given in equation number 69.9, 69.10 and 11 and 12, the equation number 1 becomes, that is the transition rate, that is the stimulated transition rate. You can call it as an absorption rate, or the that is the stimulated absorption rate, or you can say it as a stimulated emission rate, because for both these it will be the same expression. So we have W is equal to 2 pi square over 3 and epsilon naught CH square multiplied by the intensity of the beam I multiplied by absolute square of mu, which is the electric dipole moment, and multiplied by the function g of nu minus nu naught, which is the line broadening mechanism due to homogeneous broadening. The transition cross section is also defined as sigma is equal to W over F, where F is the flux of the incident beam. So W divided by the flux F of the beam is represented by I over H nu, and we are substituting the value of W over here, and then we are cancelling the common terms. Then we have sigma, which is the transition cross section for the case of the semiconductor material, is given by 2 pi square over 3 and epsilon naught CH multiplied by nu multiplied by the absolute square of mu multiplied by g of nu minus nu naught. where mu is given by the integral of uc, that is the special part of the Bloch wave function in the for the conduction band, multiplied by er multiplied by the special part of the Bloch wave function for the valence band represented by uv, and the integral is over the whole volume of the specimen. So where mu is the electric dipole moment of the electron involved in the transition, capital F is the photon flux of the incident beam. In the above equation, n is the refractive index of the semiconductor material. So you see that we have mentioned the two rules. We have mentioned the K rule for the transition. We have mentioned the delta S rule for the transition in the semiconductor material, and we have assumed that the bulk semiconductor can be treated as that of a single isolated atom, and the broadening mechanism can be treated as homogeneous line broadening. And due to these one, we have adopted the equations we have mentioned in slide number 36 and 36, and adopted for the case of semiconductor material. We have made the necessary changes, and we have derived the transition rate W expression given in equation number 69.13, and we have also obtained the transition cross section for the semiconductor material sigma given in equation number 69.14, and we have explained all the terms. So this is the end of slide number 69.